The second fundamental theorem of calculus helps us take derivatives of integrals. Okay, and usually it's when the function that we're integrating is a function of a different variable than what the boundaries of our integral are. So the rule is, if you take the derivative of the integral evaluated from a to x of this function of t, as long as a is within the continuous portion of this function, then these things basically cancel out and you just plug the x in place of the t. So here's an example. If I want to find the derivative of this function, okay, this function is now defined as an integral, okay? An integral can be a type of function. Well, as long as 1 is in the continuous portion of this function, okay, continuous meaning that there's no breaks in the area where 1 is up to x. So 1 is defined, right? I could put 1 in here and it would be defined because I'm not dividing by 0. And in fact, this entire function is defined everywhere. So it's continuous everywhere because no matter what number I put in here, I'm going to get a positive out when I square it. And if I add 1, that's still positive, and so it'll be fine. So what this means is when I take the derivative of both sides of this, the second fundamental theorem of calculus allows me to simply write that f prime of x of this function is the same thing, only now I'm replacing my t's with x's. And that would be the derivative. You could have a bunch of different things down here. Let's say this was negative x. You still do the same thing, because negative x, if I plug that in, it's still going to be in the continuous part. I'll still get this. Okay? And as long as this is just x, you can use this rule. If, however, this is not x, let's say this was x squared, all you really need to do then is change this to something that's a variable to the first power. So we're going to define u as being x squared. So then what we've got is from 1 to u of this thing. Okay, and if I'm taking the derivative of this, now that's just u, and u would be defined in here on the continuous area, same with 1. I can write it as this, okay, the derivative, I would now put u in place of that. Okay, and then I just resubstitute what u actually was, so I'll put x squared in place of u. So what this really equals would be x squared squared, which is x to the 4th, over x to the 4th plus 1. And that would be the function of x. So it's just replacing something that doesn't fit the rule, okay, because this has to be just a variable, and x is an arbitrary variable. We could use anything. So if we just replace that with a letter like u, okay, then we can do this. And this is actually similar to the technique we're going to use in section 4.5 when we start talking about integrating more complex functions. Another way we can use the second fundamental theorem of calculus is we can integrate using our regular integration rule to find what this function actually is in terms of x, and then we can differentiate to check our result. So if I use my actual rules, I'm going to distribute this t here. Okay, I'm going to integrate this from 0 to x. So I integrate it, which means I raise the power by 1, drop the reciprocal. Okay, this one I do the same thing. I'm going to evaluate this from 0 to x, which means I'm going to plug x in. So that would give me x to the 4th over 4. Okay, if I just rewrite this as over 4, and x squared over 4, and then I'm going to subtract this thing evaluated at 0. So, or let's make this 1 actually, just to make it a little more interesting. So I'll subtract it evaluated at 1, which would be 1/4 plus 1/2. This would be 2/4, so I get 3/4. So I'd have x to the 4th over 4 plus x squared over 2 minus 3/4. Okay, now that's what this function is. These are the same thing, okay? So the function equals this as an integral form, which means it equals this as just a regular form. If I want to check my answer, I'm just going to take the derivative of this and make sure I get back to this, okay? The only difference is it's going to be x's instead of t's. So if I take the derivative of this, I drop the power, which would cancel the 4 down here and reduce the power by 1, which can be x cubed. This one would go to just x. This one would go to nothing because it's a constant. And this, of course, can be rewritten as this, which is what I started with. Okay, so those are two uses of the second fundamental theorem of calculus, and that covers what you'll be required to do.